So we are continuing to talk about the concepts of voltage, otherwise known as electric potential. And the really nice thing about voltage and electric potential is it is a scalar. And now some people are going to go, oh my god, what's a scalar? But remember, scalars are actually really easy. It means that they are not a vector. So a scalar does not have direction. It's just a number. Okay, so I'm going to do a little example problem. And what I'm going to do is I'm going to have a charge here. Q1 is going to be 5 nanocoulombs, and then Q2 is going to be negative 4.8 nanocoulombs. I don't know why I made it so close. Let's make it negative 2.8 nanocoulombs. Okay, and I'm going to choose a point here. So this is going to be, we're going to call this point A, and then we're going to call this point B. And so what I'm going to do is I'm going to measure some distances, and so this is going to be 4.5 centimeters. And that distance there is going to be 10 centimeters. And then this distance here is going to be 3.5 centimeters. And then this distance here is going to be, I'll call it 8.8 centimeters. Okay, so now if I wanted to find the potential at point A, I do V equals KQ over R, and well, I do V equals negative KQ over R, and I'm going to do it twice. I'm going to do it once for 1 and once for 2. So I'm going to go V equals negative 9 times 10 to the positive 9th Newton meters squared per coulomb squared times Q1, which is 5 times 10 to the 9th negative 9th coulombs, divided by 0.045 meters. And so I'm going to get that, I'm going to call that V1A. Okay, so I've got negative 9 times 10 to the 9th times 5 times 10 to the negative 9th divided by 0.045, and I get negative 1,000 volts. Funny how that just kind of worked out, but it worked out. Now, if I've got V2A, basically I'm going to do negative 9 times 10 to the 9th Newton meter squared per coulomb squared, negative 2.8 times 10 to the 9th coulombs divided by 0.088 meters. And so I can sort of just go back in. I'm going to go back, I'm going to change this to a negative 2.8, and then I'm going to change that 0.04, I'm going to change that to 0.088, and I'm going to get positive 286 volts. So I'm going to say that the voltage at point A is going to be negative 714 volts. Now I'm going to say, because I can straight up add them, because it's a scalar, because potential difference and electric potential and voltage, because they're scalars, I don't have to do vectors anymore. I just straight up add them. And so now I do voltage 1B is going to be negative 9 times 10 to the 9th Newton meter squared per Coulomb squared times 5 times 10 to the negative 9th coulombs divided by my new distance is out to here. That's going to be 10 centimeters, so 0.1. And so I'm going to go back to that one, and I'm going to change that to 0.100, and I'm going to get negative 450. So VIB is equal to negative 450 volts, V1B. And then V2B is going to be negative 9 times 10 to the 9th Newton meter squared per Coulomb squared. And then I've got negative 2.8 times 10 to the negative 9th coulombs, and the distance is going to be 0.035 meters. So V2B is going to be, go back to, that's the one that I want, and I want to change the radius to 0.035, and I get 720 volts. And so VB is going to be minus 450. It's going to be 270 volts. So this is at so the voltage at that point is negative 714 volts, and the voltage at that point is going to be 270 volts. Okay, so now if I think about it, I might be getting the sign wrong. In fact, I'm probably definitely getting the sign wrong. But this tells us a lot about how energy moves from. This tells us a lot about what we would need to do to move a charge from here to here. And I think I can wrap it up in this video. But actually, I think I'm going to cut this video off, and I'm going to come back and do a second video on this.